What I do for Valentine's Day? I did basketball all day with my kids, and then nothing. So, here we go. Example 4. Find the slope of a graph implicitly. Ooh, this was an interesting question on the test. People forgot that slope means what? Derivative. A lot of people that drew a blank on that when I said find the slope at this point. And just remember, in this class, slope is always going to be used interchangeable with what? Derivative. So when I say determine the slope, I mean determine the derivative of the graph of this equation at the point 3, 1. So I want the derivative at 3, 1. So let's do that right now as a warm-up, and we'll just go ahead and speed this up. You guys tell me what's going to be needed on the left side of the equation. You can't until you square it. Orders of operations. Exponents come before multiplication. So you definitely can't multiply by the 3 yet. But if I want to go ahead and start taking the derivative, let me ask you this. Would you rewrite the problem?
You could.
You could. I don't know if I would. You could rewrite x squared plus y squared, quantity squared. You could expand that, distribute 3, and then just use simple power rule and maybe some product rule. I don't know. I don't know if it's a benefit. So let's just go ahead and start taking the derivative because I don't really see anything beneficial to do. So what are you going to need on the left side to take the derivative? Chain rule. What are you going to need on the right side? Product rule. All right, let's try it. Somebody tell me how to do the left side. I'm not talking today on this one. You guys talk me through this one. All right, it's going to be 6 times x squared plus y squared to the what? First times the derivative of the inside. Very nice. That's the chain rule on the left side. What about the right side? Be careful. You got constant times xy. This is all multiplication. So what rule we got to use? Product rule. Now, there's 2 ways you can do the product rule on this side. You need to pay attention because tonight your homework is going to come up. Whenever you have this product rule and you have a constant in front, you got to decide, do you want to take the constant with the x or do you want to leave the constant on the outside of your product rule? Because if you leave it on the outside, you're going to basically have this 100 right here times the product rule. And tonight that's going to matter because there ends up being a negative here. And some people say, well, I'm going to have the negative be on the outside and just distribute it later. Well, then that means it's a positive xy. You can't have it be both. The 100 is either with the x or it's not. If I do the 100 as a constant multiple and say, okay, I'm just going to take 100 times the derivative of xy, that's constant multiple rule. Or what they did last hour is they said, I'm going to treat the 100 with the x, and I'm just going to say it's really 100x times y. Is that allowed? Yeah, it's associative property of multiplication. You can associate whatever you want together with multiplication. Okay? So what do you want to do? You tell me what you want to do.
Leave it on outside.
Joe says just take it with the x. We're going to take it with the x. By the way, there's no benefit to either. It's up to you which way you like better. So if I take the 100 with the x, so what's the derivative of 100x? 100 times y. I guess the benefit to doing it the way Joe's doing it is the 100 is already distributed. But the benefit to doing it the other way, it does make it sometimes a little simpler to see the product rule. So it's kind of up to you. Plus 100x times what? 1 dy dx. So the derivative of the first times the second plus the first times the derivative of the second, depending on the order of how you want to do the product rule. Now, is everybody okay with that so far? Now, what was the next step in finding the derivative implicitly? Get the dy dx to one side. You need to treat dy dx as a variable. It is. It's unknown. I don't know what dy dx. That's what I'm looking for. So I'm just going to do like I did in algebra, and I'm going to try and get dy dx by itself on one side. Now, there's 2 schools of thought here. Because what I'm being asked for in this problem, really pay attention here, because I'm going to show you one way, and then I'm going to show you the benefit of the other way. But I'm going to do the one way first, because I always like to go the longer way first, to convince you that the other way is the better way. If I did the better way first, then you wouldn't even want me to do the long way. Okay? But here's the reality, is both of you are going to think about it both ways, so I just need to overwhelmingly convince you to look for this possibility of doing it a little bit quicker by showing you how you can tackle this problem. So let me ask you again, what are you being asked in this problem? Not just find the derivative, but find the derivative of what? You're asked not just to find the slope, but you're asked to find the slope at a specific point. So, do I actually have to have the derivative? Yes and no. You need it, but do you actually need the derivative simplified? No, I just need the derivative indirectly to find the slope at 3, 1. So, here's the two schools of thought. One is, have already found the derivative. Yeah, I've already found the derivative. I've taken the derivative. It's already found. I just haven't simplified the derivative. So here's your two schools of thought. One school of thought is to go ahead and solve for dy dx and find the derivative algebraically first, then plug in 3, 1. And that's the way we're going to do it first. The other school of thought is saying, well, I don't really have to simplify it for the derivative. And I'm not really after the actual derivative. I just need the derivative to find the slope at 3, 1. And so what some people say is, well, instead of finding the derivative algebraically, why don't I just go ahead and plug the point 3, 1 in and see if I can just get it that way. So let me show you both ways and see which way you think, and I know which way you're going to come up with this better way. So let me just go ahead and solve for dy dx algebraically. And I do want everybody to do this with me, because it's good practice, because you are going to have to do this eventually anyways. All right, so if I'm going to solve for dy dx, Mason and those guys up front are right. We need to get dy dx on one side. So how am I going to do that? Algebra. Tell me what algebra I need to do first. If you're trying to get dy dx by itself, what do you got to do? Think algebra here. Abby, you got to FOIL the left side. You don't have a choice. Because some people are like, well, I got to get dy dx by itself. I can't divide by this, because dividing by it's just going to put dy dx where? The denominator. That's not going to do me any good. So I've got to FOIL this out so I can start adding and subtracting terms. You see that? Now, I'm going to FOIL this all at the same time. I'm going to FOIL the 6 and the x squared plus y squared with this all at the same time. So this is really 6x squared plus 6y squared. Agreed? So we're going to have 6x squared times 2x. What is that? It's 12x cubed. Write this down. Now we're going to have 6x squared times 2y dy dx. That'll give me plus what? 12x squared y dy dx. You with me? Okay, now we'll do, you still with me? I'm foiling the 6 and then foiling the 6x squared 6y squared. But I'm doing it all at once. Now we got 6y squared times 2x. That'd be plus 12x y squared dy dx. Oh wait, that's not a dy dx yet, is it? Sorry.
It'd be 12 cubed. 12y cubed.
Is that good? Plus, sorry about that. So 6y squared times 2x is just 12xy squared. Now 6y squared times this one would be 12y cubed dy dx equals 100y plus 100x dy dx. Does everybody now see why we needed to do that? Because now we need to do what? Well, move the dy dx stuff to where? One side. Does it matter which side? I don't care. Pick a side, any side. Okay? Alright, I'm going to, just because I feel like it and that's what I want to do, I'm going to move the dy dx over to the right. You okay with that? And I'll move the 100y over. So here's what we're going to get. We're going to get 12x cubed plus 12xy squared minus 100y. So that took care of these three.
X squared y.
Did I not do that right?
No, I think it's x squared y, isn't it?
No.
No, it should be, because it was 6y squared times this, 12x xy squared.
Oh,
I'm just dealing with the terms without dy dx first. Equals 100x dy dx minus 12x squared y dy dx minus 12y cubed dy dx. Now, I'm going to do the next two steps together because I'm running out of room. Can anybody tell me what are the next two steps I'm going to do? Factor out the dy dx and then divide by what's left over. Can I do that in one step and everybody okay with that? So once I got that dy dx to one side, I can take the dy dx out of this by factoring. It's a GCF, it's a greatest common factor. And then I can divide by what's left over. So what I'm going to end up with, I'm going to move over here, you ready? dy dx equals, it's going to be 12x cubed plus 12xy squared minus 100y divided by 100x minus 12x squared y minus 12y cubed. Does everybody see that? Raise your hand if you do not see how we got from this last step here, okay, this last step here, to my dy dx. Now's the time to stop me. Now, one benefit before I plug in is, does everybody see something I can do? I can divide a 4 out of everything. Only because it can be divided out of everything is it a benefit. So I'm going to go dy dx. I'm going to simplify the fraction. I'm just simplifying and reducing it by 4. So I'm going to have 3x cubed plus 3xy squared minus 25y over 25x minus 3x squared y minus 3y cubed. You like that? I promise you it was helpful. Because now what am I going to do? Now I'm going to vote dy dx. Watch the notation. Ready? Everybody practice it. dy dx slash. That means what? At the point 31. That's useful to use because then you don't have to write it out. dy dx at 31. You can just use slash for at. It's just shorthanding it. All right, let's plug in 3 for x. So we have 3 times 3 cubed plus 3 times 1 squared minus 25 times 1 all over 25 times 3 minus 3 times 3 squared times 1 minus 3 times 1 cubed. All right, here we go. Let's start simplifying. All right. Top, 3 cubed, got to do exponents first. 3 cubed is 27. 27 times 3 is, I'll help you, 81. Plus, 3 times 3 is 9. 81 plus 9? 90. 90 minus 25. 65 on top. Bottom, 75 minus 27 is 48. 48 minus 3? 45. What does it reduce to? 5 goes into both. How convenient. 13/9. So we got the slope of the tangent line to this curve is 13/9. Now, a lot of work, right? Okay? Usually, implicit differentiation problem, usually when asked you to do this kind of stuff, it's on the free response, not the multiple choice. Now, they gave us the 0.31. I want to point something out. How funny. I want to point something out before I say anything else about the point. Is it would have been really interesting if they would have said, find the slope when x is 3. Like if they would have said x is 3, then it's a lot more involved. It's even more involved than what we just did because you'd have had to find the derivative, then plug the point in. But the problem is you don't have a point. You only had x equals 3, so how would you find the point? Plug in the original. But let me tell you the conundrum you would run into plug into the original if they just told you x equals 3. It is very possible that you would have gotten how many different y's for answers? That you might have gotten 2 y answers. Okay? And then if there would have been a y to the 4th in there, you could have up to 4 points. Probably because this thing is looking like an ellipse. And it's not a function, doesn't pass vertical line test, so there's probably 2 points where it's 3. So just be glad I told you 3-1, because if I didn't, you would have had to find the point, and there might be 2 points, which means you would have had to plug in what? How many slopes would there have been? 2 different slopes. You would have had to plug in 2 different points. Or if possible, it could be up to 4 points. It could be up to 6 points. It just depends. Plus a differentiation, when they just give you the x value, there might be more than 1 point to find the slope at. Okay? But be glad I just gave you 3-1, so I gave you the specific point I wanted. Now, look at all that work. Everybody stare at it. 1, 2, 3, 4, 5, 6 steps, essentially. I'm going to go back to step 1. Remember what we said? In step 1, did we have the derivative? So did we necessarily have to take software algebraically to plug in the point? No, once you took the derivative, you could go ahead and start using it. So watch me, because I'm going to reduce this from 6 steps to 3. You ready? I'm going to plug in the 0.31 right now. Here we go. 6 times 3 squared plus 1 squared. 2 times 3 plus 2 times 1 dy dx. And as you plug it in, some of you are so good you might even start simplifying this as you go because it's just numbers now. 100 times 1 plus 100 times 3 times dy dx. Now watch. I'm going to do this last stuff. A lot of it in my head. Here we go. 3 squared? 9 plus 1? 10 times 6? So we got 60 there. Times 6 plus 2 dy dx. Equals 100 plus 300 dy dx. Alright, I'm going to do the rest of it in one step. Are you ready? Okay? Not yet? Tell me when you're ready. I'm about to do the rest of the problem in one step. Okay, with me? We can do this. This is simple algebra now. Because we're going to distribute a 6, and as we distribute a 6, that's going to give you what?
No,
360, right? Then I'm going to subtract the 100 over, so that's going to give you what? So we got 260. Equals. Now we got the 60 times 2, which is what? 120 dy dx. Move the 120 dy dx over here. 180 dy dx. Okay? And some of you might even show less work because you might have already started simplifying that up there. But you get dy dx is equal to what now? 260 over what? 180. Now watch. Zeros cancel. 2 goes into both. 13 ninths. So you could save yourself a little bit of work, basically 4 steps versus 5 to 6 steps. So you could save yourself a little bit of work. And I think most people like simplifying. Students simplify better with just numbers versus algebra. Okay? They usually do orders of operations better than they do the algebraic operations. All right, last thing I'm going to do with implicit differentiation. Are you ready? And I got about 24 homework problems tonight, so I tried to really be sensitive. There's a lot going on the next 2 weeks, and I'm going to try and I need to do homework every night most of the time, but I'm going to try and keep it for the next 2 weeks below 30 problems just because there's so much going on the next 2 weeks with wrestling and basketball and gymnastics and hockey and then science, just a lot of craziness next 2 weeks. And then as the trimester ends, then it's just going to be, I'm going to be all on assault on you. Okay? Just know it's coming. And for like 9 weeks of your life, you're going to feel like you're in research paper mode if you had Miss Enemy. Okay? Y'all never got to experience her. All right, find the second derivative implicitly. Okay? Huh? All right, anybody doing a research paper right now? Oh. Yeah. Remember those days. All right, find the derivative. All right, I'm going to teach you how to do this. Now, Amy actually already knows how to do this. But she jumped into one of her problems. And she's going to be like so enlightened the whole time we do this. For the rest of you, just hold on. All right? Second derivative implicitly, there's nothing new to teach you except for some algebra stuff and some stuff to look for. There's what I call a double substitution. I don't know if any other teacher calls it that, but that's what I call it. I call it a double substitution. We're going to show you how to look for that and what it is that you actually do. But just rest assured, there's no new calculus. Everything I'm going to teach you right now is all algebra based because you already know how to do a derivative and you already know how to do a second derivative. You already know how to do implicit differentiation, so nothing new calculus related. All right, so let me show you what you're going to do. I want everybody right now to find the first derivative as quickly as you can. I'm going to give you 30 seconds because this one's simple. By the way, this is the most popular first derivative done on the AP exam on the multiple choice. Okay? So quick. Don't forget your dy dx. Remember, you got to do y implicitly. Hey, nobody look up because I'm going to start doing it up here. Don't look up. Just look down the paper, see if you can get it all the way down to dy dx, and then look up and you can check it. All right, now you can look up. dy dx, negative x over y. Raise your hand if you got negative x over y. Good. We can do implicit differentiation. This is the most popular problem on a multiple choice on the AP exam. Okay, they always do circles. And just be glad they do circles because they're real fast. In fact, you could go ahead and memorize it. It's always negative x over y. If you get x squared plus y squared, it always ends up being negative x over y. So this right here is implicit differentiation, first derivative. Now let's talk about the second derivative, all right? Can I go ahead and erase the first derivative work?
Yeah.
Okay, so I'm just going to write down, we got dy dx was equal to what? Negative x over y. Okay, second derivative. Tell me what's all going to be involved in the second derivative. Nothing new. Come on, tell me what's going to be involved here. Quotient rule. You're still going to have to, when you get to y, you're going to have to take the derivative of y implicitly, right? Because we got an x and a y still. Y is not solved for. Wait a minute, why would I need y anyways? Because I'm talking about a second derivative now. I usually don't have y's in my first derivative. So that's going to create a problem. Let's think about it. When I start doing quotient rule, you're going to get to y, and what are you going to have in your second derivative that I've never had before? You're going to have a dy dx in your second derivative, and we're going to have to deal with that. Okay? Just know that it's coming. Now, let's talk about this over here. How do we take the derivative of dy dx? You do it implicitly like you did y. We're going to do it implicitly. So what is the derivative of dy dx? What's the derivative of dy dx? d squared y over x squared. That means the second derivative of y with respect to x a second time. That's all you do. You just do it symbolically. We don't know what d squared dy, or d squared y over dx squared is. We just know this is represented symbolically of the first derivative. So we're doing it implicitly, saying, okay, if this is the first derivative of y, implicitly this is the second derivative of y. It's just symbolic. It's just notation. Okay, now let's go to the side. All right, tell me how to do it. It'd be negative 1 times what? Y. We're using quotient rule. Minus. Now I'm going to go ahead and put negative x. Let's go ahead and write that down. Times what? Times what? Times the derivative of the bottom, which is going to be 1 dy dx. Don't forget the dy dx. And some people are like, do I have to put the 1? No, you do not have to put the 1 anymore. It's up to you. I always do, usually, but in this case I won't. And then over y squared. Don't forget over y squared. I can clean it up a little bit, just for good measure. We'll have negative y plus x dy dx, okay, over y squared. Now, that is your second derivative, and there's nothing wrong with that. You did it correct, and if this was free response, you'd probably get some points. You probably get a point for it. But the next couple of points you're going to get from doing the next two things, which I call a double substitution, and you always need to look for both. One of the substitutions will always be there. Listen to me. One of them will always be there. The second one is not guaranteed. The first one is. What you're going to do, where are we at right now? Where are we at in the problem? We're at the what? We're at the simplified version of the second derivative. We're at the second derivative now. We're going to walk backwards through the problem, and we're going to look back through the problem and see if there's some things that can help us substitute for some things in here that we don't really want to have in here. So I'm going to tell you, when you have your second derivative, you don't want a dy dx in there. So your first substitution, walk back one derivative. Go back a derivative. We're at the second derivative, so go back to your first derivative. And the first thing you're going to do, and you're always going to do this, and it's your first substitution, you're going to do what I call the dy dx substitution. You just plug in what the derivative was. You know what the derivative is. So I don't want to leave this random, oh yeah, by the way, I'm going to take negative y plus x times dy dx. Well, what is dy dx? The reason you do this substitution is because I don't want to have to go back and figure this out separately. Let's have it in our equation. So what we're going to do is we're going to have, we'll come up here. Ready? So we're going to have d squared y over dx squared. It's going to be equal to negative y plus x times, what is dy dx? That's your first substitution. That's the one you'll always be able to make. You'll always be able to do that one. Because if you get into implicit differentiation and there's a y in your first derivative, then your second derivative is going to have a dy dx in it, and you're going to be able to plug back in for it. Now, if your first derivative doesn't have a y in it, you won't have to worry. Okay, but if your first derivative has a y in it, when you go to your second derivative, you're going to have a dy dx, and you'll always be able to make that substitution. All right, now, look what's going to happen here. I'm going to end up with negative y plus x squared. Sorry, my bad. What's supposed to be? Negative y minus x squared over y squared. Now, after you do your dy dx substitution, simplify as much as you can. Right now, what can I simplify? Before you do the final substitution, you need to simplify. What can I do here that I don't like? What is an eyesore to you right now? All right, let's get rid of the eyesore. So how do we get rid of the eyesore? Multiply top and bottom by y. Quick way to get rid of it. So then we're going to end up with negative y squared. Does everybody see that? Minus what? X squared, because those y's are going to cancel over what? Oh, you're so there now. Now, this final substitution, you got to look for it. We already looked to the dy dx, the first derivative. Now go back to the original function. Can anybody tell me how I could get creative and use the original function to make a final substitution to make this even simpler? If you factor out a negative on top, you're going to end up with y squared plus x squared over what? And then what's the original equation? Look at the original equation. What's the original? It's x squared plus y squared equals 25. How can I use that to make a final substitution? I can take the x squared plus y squared out and replace it with... Yeah, so the answer is negative 25 over y cubed. Is that a simple second derivative or what? You would actually only need the y value if you wanted to...
If we didn't get it to work out where it was like y squared plus x squared, would that be our answer?
Yeah, sometimes you won't be able to make the original equation substitution. Sometimes there won't be anything creative you can do to make it simpler. The original equation substitution only happens, I can't even tell you a percentage. It happens sometimes is all I can say. Now the dy dx one always happens. But the original one is sometimes, sometimes not. Okay? Stop there. I've got one more thing to do today. Okay? And it's real short. Take your calculator out. Let me pause this.